going to go through several problems for the Nyquist diagram. And so this first problem here, first what we'll do is take a look at the root locus, as that will help us in some aspects with the Nyquist diagram. So the root locus looks like this. We have a pole. We have a pole to origin, we have a pole at 3. And in this case, as far as the real axis is concerned, the root locus will exist here. It's always directed away from these poles, so this direction. And it's going to break away right in the middle. So if this is 3, it's going to break away at 3 halves. And you have one branch upward and one branch downward. So you can see that this system is always unstable. Poles are always in the right half plane for any positive value of gain k. Now let's do the Nyquist diagram. We start out with the S-plane contour, and what we have to do is route around this pole to origin. So we have the pole to origin there. We're going to route around it, go up the j omega axis all the way to j infinity. This point here is infinity. This point here is minus j infinity. And this is the direction. So we'll start here, and any point on this little contour, enlarge the small contour. It looks like this. Any point on that contour can be described by S, right? It's the S plane equals rho e to the j theta. So theta is this angle in here, and rho is the size of the vector. What we're going to do is let rho go to 0. And we'll let theta start out at 0. In other words, the little vector starts out horizontally. Okay. And theta is going to vary between 0 and 90 degrees. In other words, when the vector is horizontal, theta is 0. When the vector is vertical, theta is 90. Okay, so the first thing to do is map points on from this portion of the S-plane contour into the plane of the open loop transfer function. Plane of the open loop transfer function is a GH plane. So we can do a little calculation here. We're going to set in the open loop transfer function, which is our GH, is just basically this here. We're going to replace S by rho e to the j theta. All right, so we have K over rho e to the j theta, and then we have minus 3 plus rho e to the j theta. And so what we're going to do is let rho go to 0. So we take the limit of this as rho goes to 0. Okay. And what you can see is that inside the parentheses here, this is just going to become minus 3 because rho is going to 0. And here, rho going to 0 in a denominator causes the ratio of k over rho to be infinite. And e to the j theta in the denominator is e to the minus j theta in the numerator. So this becomes equal to infinity at e to the minus j theta. Actually, it's I have to take into account that minus sign there, the minus 3 here. Okay, so it's going to be actually let me put it this way. You've got an infinite value e to the j theta, and minus 3. So minus 3 can be represented by 3 angle plus or minus 180. So if you say minus 180, now you've got that. Now you bring these two together. Actually, we can write this as 3 e to the minus j 180. Okay, minus 3. Okay, we can combine these two exponentials here, and it's theta minus 180. And when we bring it into the numerator, just change the sign, right? So you've got infinity over 3 is still infinity. So you've got infinity e to the j 180 minus theta. Okay. Do you see the math there? Right. We've got in parentheses the rho e to the j theta is going to go away because rho is going to 0, so all we're left with is minus 3. The minus 3 can be represented as 3 e to the minus j 180. Okay. And here we have the e to the j theta. We combine these two exponentials, and we've got, in the denominator, they would be theta minus 180. Bringing them into the numerator makes them 180 minus theta. Yeah.
How do we take account for the negative 3?
Where the minus 3 comes from?
Where did it come from, and how did you get rid of the negative portion of it?
Oh, so the minus 3 is from here.
Okay.
Okay. And then, you know, I want to express minus 3 in terms of magnitude and phase.
Okay.
Right? So it's got a magnitude of 3 and a phase of 180. That's minus 3. It's along the negative real axis.
If the rho e to the j theta was also on the outside of the parentheses, didn't that make the entire denominator 0 when that's approaching 0?
Yeah, so you're talking about this, right?
Yes, yeah. Well, how come that didn't cancel the entire denominator? Like, get rid of the 3 as well.
Well, rho itself is going to 0. And the phase, I can't get rid of the phase. I shouldn't get rid of the phase.
You just think it's approaching 0, but you're not actually just sticking the 0 in
Yeah,
there.
you know, it's approaching 0. It's approaching, and so the ratio is approaching infinity.
Okay.
And the phase.
Oh, so you accounted for that by just putting an infinity on the numerator and then keeping your current stuff on the denominator?
Yeah, right.
Okay.
I got k over rho, that's going to go to infinity.
Uh-huh.
The e to the j theta denominator.
Okay. So you just took the k over rho and sort of kept that separate from the rest of it and made that infinity, and then just kept the rest normal.
The,
Okay.
The k over rho becomes infinite. E to the minus j theta in the denominator becomes e to the j theta in the denominator becomes e to the minus j theta in the numerator.
Okay.
And well, I combine these two together, right?
Mm-hmm.
You know, the 3 basically goes away because infinity over 3 is still.
Right. Right.
To combine these two, you've got theta minus 180. Bring it into the numerator, you've got 180 minus theta.
So this is just a little bit of like manipulation, knowing how to work with like limits.
Yeah.
Yeah. All right. And then everything, you're trying to get everything in the numerator into just one term, huh?
Yeah.
Okay.
Finally, I want a magnitude and phase.
Okay.
And so here theta is varying between 0 and 90 degrees, right? We said really all we have to do is let's say we'll start here and move to there, and then move up the j omega axis, and then move around.
Okay.
Okay. So what this accounts for here is movement from here to there.
Right. Okay.
So when we start drawing our Nyquist diagram, with theta equal to 0, you've got infinity angle 180.
Mm-hmm.
Okay, which is a point here, say. Where, you know, if you break the axis, you've got minus infinity.
Mm-hmm.
Okay, minus infinity, and then we let theta increase to say 45.
Okay, and then just check again with that value. You're plotting points on this on the Nyquist diagram,
Now
right?
plotting points on the Nyquist diagram.
Okay.
This is the GH plane.
Okay.
Imaginary versus real.
Mhm.
Okay. And so I start out with that point, corresponds to theta equals 0. I increase theta to 45. That's going to give me 180 minus 45, which is 135. So I have this angle 135 and at an infinite distance. Right? So I have a point here, and then finally let theta equal 90.
Mhm.
I get 90 degrees. 180 minus theta is 90 degrees. So what I have is this here. And this is the direction that corresponds to movement in that along the
Right. Okay.
path here. So I've got part of the Nyquist diagram. Okay. The next thing I need to do, so this is segment 1, say, and then I need to climb up segment 2. That's where S equals j omega. Okay. And for that, you have a frequency response, right? Wake up. I better wake up. Okay, so here's the frequency response. That's for 1 over s squared minus 3s, okay, which is what we have here.
Mhm.
The frequency response, I start with a low frequency. Can't start with 0 because we had to avoid the pole at the origin, right? We have the pole here at the origin. Okay, let's start with a small positive value frequency. I get the very large magnitude, and the phase is minus 179, which is basically starting here. Okay. Small. Sorry. Where are we starting? That's 179. Am I talking about the same system? Oh no, this is not the same system, right? It's s plus 1 over s squared. I want a different one. That's right. So I called it. One. That was example 1. And so here we have numerators 1, denominators s squared minus 3s. And so I execute that and look at the frequency response. So here's the frequency response. You see that it starts at very low frequencies. The magnitude is large relative to these other values here. And the phase is minus 269, right? So minus 269 would be all the way around here. It's a point basically up in this region here, okay? And then you take more points. Let's say take frequency at 1/10, the magnitude is 3 now. It's still very close to minus 270, so let's take a larger frequency 1. Magnitude is 0.3 and the phase is minus 251. So you can see that this point up here, remember, is at j infinity, right? It's an infinite distance away. So the point here is not to try to draw something that's super accurate. Really, finally, what we want to do is determine the n value, okay? And so we had 0.3 and the phase was minus 251 or so. Okay, what was that? 0.3. 0.3 minus 251, right? So that might be something like this, 251, again, it's magnitude and phase, right? Minus 251 for phase and magnitude of 0.3. What you can see is that as the frequency increases, the magnitude is getting smaller and smaller, and the phase is approaching minus 180. That is minus 188, minus 183, minus 181, which means that it's coming down like this. Coming in, let me make it. Coming in like that, with a phase that is slightly greater than 100, well, it's in magnitude, sorry, the phase itself is minus 180, minus 181. Small magnitude, phase of minus 181. Okay, so we're just plotting points. We plot several of the points there, and we got that. And so what we've done here is map this segment here, segment 2, into segment 2 prime. Okay, and then what we need to do is map this segment here. The segment is at an infinite distance away, right? In other words, the vector from the origin has a magnitude which is infinite. And so what is the corresponding value of the GH? Anybody? When S is infinite, 0. So this point here would be, say, 3 prime, or this, I'm calling it 3. And just as the below the horizontal axis, these points are complex conjugates of the points above. The complete Nyquist diagram can be obtained just by taking the mirror image about the real axis here. So this came up around like that, then it came down like that, and then the complete Nyquist diagram will look like this. Okay, so you see, after it got, after we accounted for points on this infinite radius semicircle, we start up the j omega axis at minus j infinity, and we go up towards 0. So that gives us these points here. Okay. That's where we started. That's where we ended. Yeah.
So the segment 2 prime, that's basically that right there. That's only on 2 prime, right?
Say that again.
That display right there is only displaying the frequencies, magnitudes, and phases of segment 2.
You're talking about the frequencies.
Correct.
The frequencies start very small and go very large.
Is that only dealing with segment 2?
Giving us
Would if I were to plot all those points right there, would that give you that whole graph?
that would give one segment. That would give one segment. Okay, that's this segment here.
Okay.
Right here, S equals j omega. Right. So segment 2 here maps into that according to that frequency response tabulation. Yeah, segment 2 maps into segment 2 prime. Okay, so that now the point minus 1 is inside there. Notice that what I have done is find the Nyquist diagram for any k greater than 0. If you start with k equal to 1, you're still going to get this infinite radius contour here. Okay. With k equal to 1, this might be shaped a little bit differently. In other words, it might come out a little bit more or it might come in a little bit more, but it's always going to come in at an angle of 180 degrees. Okay. So the shape, basically the shape is not going to change. Okay. And therefore, the -1 point will always be enclosed for any positive value gain k. Okay. There's no way that this contour that we have here could exclude the point -1. Right. In fact, what we have here is, what is n? That's the question. What is n equal to? We have one clockwise encirclement of the point -1. That is our n value. N is equal to 1. What is p equal to?
Where do you get 1 point -1?
Where is the y -1?
Yeah, 1.
It goes back to the mapping theorem. We started out by considering the mapping from this contour here to the f of s plane contour, which is 1 plus gh. Okay, and there what we did, if we looked at this contour, we considered the net number of encirclements, clockwise encirclements of the point, the origin. So if you're dealing just with gh, right, the difference is -1. In other words, gh equals f of s minus 1. So instead of counting encirclements about the origin of the f of s contour, we're going to count the encirclements about the point -1 of gh, the open loop transfer function. Okay, so it goes back to the mapping theorem.
And then how did you come up with n equals 1?
With n equals 1. N, remember, n is the number, or the net number of clockwise encirclements of the -1 point. Okay, -1 is here. We have, what do we have? Am I right or wrong? It's clockwise, right? It is clockwise. Right? So n is equal to +1. Okay. And so what we want to do here is determine whether it's stable or not. From this diagram, from this root locus, we know it's always unstable for k greater than 0. Okay. What is p? It's the number of right half plane poles of the open loop transfer function. There's one right half plane pole. That's equal to 1. Z is equal to n plus p is equal to 2. What that means is that we have 2 right half plane poles of the closed loop system. Equivalently, we have 2 right half plane zeros of the open of the characteristic equation 1 plus gh, right? And 1 plus gh is the denominator of the closed loop transfer function, 1 plus gh. Okay. 2 right half plane poles of the characteristic equation, which is 1 plus gh. 1 plus gh, I'm sorry, like that, poles of the closed loop transfer function. Okay, and that's the same as the number of zeros, right? I can write this as the number of zeros of 1 plus gh. 1 plus gh is the denominator of the closed loop transfer function. Therefore, it's equivalent to the number of right half plane poles of the closed loop transfer function. Does that make sense? Okay, so we've analyzed this system by, first of all, we wrote the closed loop transfer function, and we found the roots. And we found that the roots were in the right half plane. Therefore, it can't possibly be stable. Okay. Then we took a look at the root locus. Again, from this, we see that it can't be stable for any value gain k. The roots are in the closed loop transfer function poles are in the right half plane. Okay. And then we plotted the Nyquist diagram using that frequency response. First, we started out with mapping this segment 1 here, or enlarged here. And what we found was this expression here, where theta varies from 0 to 90 degrees, right? 0, the vector is horizontal, 90 is vertical. And we plotted those points. Those points were right here. Right here. Okay. Then we used the frequency response tabulation to get these points here. Then this point here was corresponding to the points on the infinite radius semicircle. And so you've got infinity in the denominator, so the ratio is going to be 0 to get that mapping to the origin. At that point, you just take the mirror image about the real axis. So this flips downward, right? All we really had to do was map this segment, followed by this segment, followed by this segment here. Okay. Any questions or yeah?
I was working on the first problem of the homework, and I guess it kind of gave us sort of a chart of like in the points, and we were like plotting it. Would it make sense to do like a logarithmic scale chart? No.
No, you don't have to do a Bode diagram. I think that's what you're.
No, this like a logarithmic scale for that, because the points went from like 1 to like 300, and I mean you couldn't really accurately draw a scale like that. You know what I mean?
As a matter
So
of
like,
fact,
does it make sense to do log?
Yeah, you could like
Okay.
on the horizontal and vertical axes, right?
Yeah, because it was just for a finite set of points or whatever, but it was from a really large scale. It's like pretty
Logarithmic
small.
Makes sense.
Okay.
Right. So, but then the bottom line still.
It makes it look a little different, but I mean, it seemed to all fit.
Yeah. Right.
Better.
So
Yeah.
The bottom line is counting the net number of clockwise encirclements about the point minus 1.
Okay. And there was 1, I think.
Okay, 1. Okay. In this case, we had 1 clockwise encirclement, and we had 1 right half plane pole of the open loop transfer function.
In this one, yeah.
Yeah, and so that gave us 2 for Z.
Okay.
Okay. So then let's do another example. What we'd like to do, so this system here is unstable, right?
Right.
We could stabilize it. We could put a lead compensator in there. In other words, make that K S plus 1. Okay, and so how does that change? How does that change the root locus plot? Right? Instead of being vertical like this, we have now the pole to origin of pole 3 and a pole at minus 1. So let's say that, 0 at minus 1. Minus 1. Okay? It's going to exist here. It's going to exist here. It's always directed towards that 0. And, it's going to break away, and it's going to re-enter, right? Number of asymptotes. There are going to be. There's going to be 1 asymptote, right? It's the difference between the finite zeros and finite poles of the open loop transfer function. So there's 1 asymptote, and that 1 asymptote is along the negative real axis. Okay. So it's going to break away and somewhere here. is going to re-enter, okay. One branch is going to move towards, or be directed towards that finite zero, and the other branch towards the zero at minus infinity. Okay, but you know, why draw the root locus? The reason is that you can see that there will be a value of gain k for which the system is marginally stable. Okay, and in other words, and in fact, you can see that if that gain k exceeded that value, the system would be stable. Okay, so what we like to do is draw the Nyquist diagram. And so here's still the S-plane contour, same one. We still have a pole at the origin there. This no longer applies here. Okay, and so we can get rid of this. And it's going to look a little different now. And what we'll do is let the gain k equal to 1, basically. Okay, and we'll draw the Nyquist diagram for this case here. So again, what we need to do is move along this segment, and here what we'll have is rho e to the j theta plus 1, right? So s plus 1, the s has been replaced by rho e to the j theta. The denominator is the same. And we're going to let rho go to 0. It's going to be, this term here will go away, because rho is going to 0. All we have left is 1. And in fact, we said that k is going to be equal to 1. And so we get basically the same result, okay? Because we have 1 over rho. Rho goes to 0, we've got infinity. We combine these two with this one going away, right? We just got the minus 3, which we represented by this, okay? And combining the phases, we get this. We get exactly the same thing, okay? And so the first part of the Nyquist diagram will look the same. Okay, it goes up to j infinity. And now the next part of the diagram, we can take a look at and here I want to call 1A, and 1A is right here. And so I execute 1A and look at the frequency response. Okay, so you see that at low frequencies, it's very large in magnitude, in phase of minus 269. Bless you. As the frequency increases, the magnitude is getting smaller and smaller. And the phase, notice that the phase is approaching minus 90 degrees, minus 92 degrees. In fact, minus 90 degrees it's approaching. So you can see that it goes through starts near minus 270. Notice that that there is a 180 degree phase crossover point. In other words, when the frequency is 1.732, the magnitude is 1/3, and the phase is minus 180. That is the 180 degree phase crossover point. In other words, it looks like this. Let this point here be minus 1. It looks like this. where that right there is minus 1/3. Right? Right, this is 0.33 at an angle of minus 180. That's minus 1/3. Okay, and I'll show you analytically how we can get that point. Okay. So it looks like this. It's coming downward like that, around like that, and ending up with a phase close to minus 90 degrees, right? In other words, take a point here from the origin, the vector from the origin to that point there, the phase is slightly greater than minus 90 degrees, right? Minus 92. Okay. And so this is the shape of the Nyquist diagram, okay? And then the rest, you see we have S in the numerator, S square. When S is very large, basically we have S over S square, or S over S square is equal 1 over S. And so what I'm trying to show you here is that points on this infinite radius contour again map into the origin. 1 over very large, 1 over infinity is small, is 0. And so this is our segment 3 prime. This is our segment 1 prime, 2 prime, and 3 prime. And once we have mapped the points above the real axis in the from the S plane to the GH plane, we just have to take the mirror image about the real axis here. And so now this one is going to be the same, right? In other words, it's going to look like this. So the direction like that, right? So it comes in like that, comes around. And the question is, what is the value of n in this case? Yeah, actually we have one. If you start here, you go around like that, that's one counterclockwise encirclement, right? Counterclockwise. And if you, so if you continue, there are no more encirclements. Okay. So you can start, a convenient place to start would be here. You have to go according to the arrows. Right? There's one counterclockwise, and then coming around, no more encirclements. N is equal to minus 1. P, what is P equal to? Number of right half plane poles of the open loop transfer function, 1. What is Z equal to? N plus P, 0. Okay, that means there are no right half plane poles of the open loop of the closed loop system when K is equal to 1.
So you're counting the counterclockwise portion of the rotation, and then when you continue, isn't that considered one clockwise also?
But it's not enclosing any the point minus 1.
Why is it not enclosing?
Oh, I'm sorry. I was wrong, right? So I was wrong. Right? I was thinking minus 1 was in here. Minus 1 is actually here, right?
Yes. So would that mean that n equals 0?
So so if minus 1 point is here, this one contributes nothing. This one contributes 1 clockwise encirclement, right?
Okay.
And so this is plus 1. And so this is equal to 2, right? Which means system is unstable. The closed loop system is unstable, and there are two right half plane poles. You can see that over here, right? That k equal to 1 corresponds to a point right here somewhere, and its complex conjugate down there. Two right-half plane poles of the closed loop transfer function. In fact, what we can do is do the Rouse test. Right? Let's do that right here. For the Rouse test, we need 1 plus GH, right? So 1 plus, and we'll do it for the general case when we have a K in there. Okay, so for K in there, what we'll get is, let's see, 1 plus K s plus 1 over s minus 3 equals 0. That's our characteristic equation. So we get s squared plus K minus 3 times s plus K, right? S squared minus 3s plus ks plus K. So that's K minus 3 times s. Okay, and so this you can see that you can do the Rouse array, or you can even just take a look at this, that when k is equal to 3, what we'll have is s squared plus 3. Okay, let me write the array. S squared, s to the first, s to the 0. We've got 1 and k minus 3, and k. Right? That k just moves down there. And so that for stability, if we're talking about stability, there should be no sign changes. So k greater than 3 for stability. Okay. If k is equal to 3, we can form the auxiliary equations, right? We go back to the previous row with k equal to 3. We got s squared plus 3 equals 0. That's the auxiliary equation. So you can see from this that s is equal plus or minus j square root of 3. So what can we say from this? We can say that if k is greater than 3, the system will be stable. The poles will be in the left half plane. Okay. If k is just equal to 3, we can determine, right, for this with the k in there, we can determine that we have it's marginally stable, right? It's marginally stable with k equal to 3. It will go through the minus 1 point, because what we said earlier was that if the open loop transfer function, if the Nyquist diagram goes through the minus 1 point, then typically the system is marginally stable. Okay. So with k equal to 3, it goes through the minus 1 point. So it looks like this, right? Comes up like that, comes down through the minus 1 point and around. Okay. And then there's a mirror image like that. Okay. So that's for k equal to 3. If k is equal to 1, that's what we have here, right? We drew this Nyquist diagram for the case where k was equal to 1. Okay. If k equals 1, all that does is compress the diagram, right? From 3, k equals 3, k equal to 1, compresses it by a factor of 3, right? And therefore, this point right here will indeed be minus 1/3. From minus 1 by a factor of 3, minus 1/3. Okay. So this is a way of finding the 180-degree phase crossover point of the Nyquist diagram. And this root locus here tells you that indeed you do have a marginally stable, the system could be marginally stable, specifically for k equal to 3. See, by taking a look at this diagram here, you can see the possibility that the system could be, for a certain value gain k, could be marginally stable, right? J omega axis, closed loop transfer function poles. And so on that basis, you perform the Rouse test here. You find the gain k for marginal stability, and you take the negative reciprocal of it to find this 180-degree phase crossover point there. Right? You just, from marginally stable, squeeze it down, compress it by a factor of 3. This point goes from -1 to -1/3. Okay, so what we have done here is use proportional plus derivative type compensation. That's PD compensator, lead compensator, type of lead compensator, to stabilize a system. And if the gain k is greater than 3, you can see from the root locus here, right? K is equal to 3 at this point. If the gain k is greater than 3, you've got a stable closed loop system. So what that means is that if you make the gain k equal to 10, it's still going to be stable for any value gain k greater than 3. Right? It's just that this point here is going to move further and further to the left. Sorry, to the right. Okay, further and further away from the -1 point. Okay, and so last time we were talking about the gain margin. If the gain k is equal to 1, by what factor could we increase the gain k such that it becomes marginally stable? 3. And now 3. Yeah, that's the gain margin, the margin of stability. Oh, and now by the way, if you make the gain k equal to 1, it passes right through the -1 point. If you make the gain k less than 1, it basically corresponds to points in the right half plane. Okay, so gain k less than 1, what happens is that this point is moving beyond -1. Okay, if it moves beyond -1, in other words, the -1 point is going to be inside here. Okay, what is n equal to now? -1, right? -1, so this is +1, and n is equal to, z is equal to 0. Am I saying this the right way here?
If k is greater than 3, then it'll move it inside that little loop.
If k is greater than 3, we'll have a stable system, right? If k is equal to 1, we'll have a marginally stable system, right?
It's 3.
3.
If k is equal to 3.
Oh yeah. If k is equal to 3, we have a marginally stable system. If k goes down to 1, in fact, anything less than 3 is going to be unstable, right? So, in other words, -1 point is still there. So, how about the gain k? K equal to 1. If k is equal to 1, it's marginally stable. If k is less than 1, go ahead.
If k is 3, then it's marginally stable, right?
Yeah, I think I made a mistake saying something earlier. If k is equal to 3, it's marginally stable.
At -1.
It goes right through the -1 point.
Okay. And then if it's less than that, then it's unstable.
If k is less than 3, then it'll be unstable. So if k is equal to 2, k equal to 1, k less than 1, it's unstable.
Now at that point, let's say when k equals -2, are you encompassing that -1 into that counterclockwise circle?
If k equals 3, it goes right through, right?
Right.
If k is less than 3, it just moves this point. Which way?
To the right. When k is 1 to the right, the lower goes to the right. It should be moved 1 to the left on the opposite.
To the left or right? Left, you say. Okay, so if k becomes equal to 2, right? If k becomes equal to 2, then this -1 point will be enclosed. So the -1 point will go inside there. For any value k less than 3, k less than 3, this is the situation. -1 is right there. Okay? And in this case, we have one counterclockwise that
Should be greater than 3, wouldn't it?
sorry,
Should be any value k greater than 3, isn't that right?
let me get this confused now.
When it's less than, -1 is outside of that little loop.
Say that again?
When k is less than 3, -1 is on the outside of the counterclockwise loop.
Okay, so k is
That's k less than 3.
k less than 3.
Yeah.
Okay. This diagram here. Okay. So if k is, and for that one, we have, what, the n value is equal to 1, right? Yeah, okay. And so z is equal to 2. When k is less than 3, we have 2 right half plane poles. Okay. If now k is greater than 3, turns out that the -1 point is going to be inside, right? So the -1 point here, k is greater than 3. Okay. And so there, what is the n value? N is -1, right? So n -1, p equals 1, z is equal to 0. So stable, okay? For any k greater than 3, we have this. For k less than 3, we've got this here. Stable system, unstable system, k equal to 3, marginally stable system. Okay. So we use this leak compensator to stabilize the system. Okay. So let me go through another possible problem here. Let's do this one. We have k over s squared. Okay. What does a root locus look like for this? Up and down, right? So it looks like this. That and that, right? We have the 2 poles there. In other words, the system is marginally stable. And you can see that easily. The C over R is equal to K over S squared. 1 over 1 plus k over s squared is equal to k over s squared plus k. Okay, so from the denominator, you can see that it oscillates at the frequency which is equal to the square root of k. Okay, and so what we'd like to do is stabilize the system. First, let's take a look at the root locus for this particular system here. Again, what we have to go through is, since we have two poles, our S-plane contour has to go around like that, up the j omega axis, around like that, back up. Okay, and so same kind of thing, S equals rho e to the j theta. When we put it into the open loop transfer function, we get k over rho e to the j theta quantity squared, right? And we replace S by rho e to the j theta. And we're going to take the limit as rho goes to 0. What that is infinity e to the minus j2 theta. And the reason for the minus 2 theta is that this becomes is a square, right? So you get j2 theta. Bring it up into the numerator, it becomes e to the minus j2 theta. So you got infinity angle minus 2 theta, where again theta varies between 0 and 90 degrees. Okay, and so the S-plane contour in that case looks like this. See, with theta equals 0, it's infinity angle 0, so it starts out here somewhere at infinite distance. Theta equal to, say, 30 degrees, you get minus 60 degrees, and so you get a point here, say. Theta equal to 45, you get minus 90, and so you get a point here. Theta equal to 60, you get 120, and theta equal to 90, you get minus 180. So it goes from infinity angle 0 to infinity angle 180. So it wraps around like this. Okay. And so this point here is minus infinity. Is there any problem to see that? You see that? Okay, so what we've done, we've mapped this segment here. This is segment, say, 1. This is segment 1 prime. Now you go up the j omega axis. And going up the j omega axis, now we're talking about this here. Okay, replacing S by j omega here, right? To S equals j omega, so you got j omega quantity squared. That's equal to minus k over omega squared. And this is a negative real number. Negative real number for any positive value gain k. Okay. And so as the frequency increases from small to large, this starts out at large, getting smaller and smaller, while the phase is always 180. Okay, so it comes in like this. Right? Comes around like that, in like that. See, you're just working with this, where k is positive. So this is always negative here. And it's starting at very large when omega is small, starts out here, and becomes very large when omega is starts out large and becomes very small as omega gets very large. So it moves in like that. And then, you see, you've got S squared denominator. So this segment here maps into the origin again, because you basically got the division by S squared. So this is our segment 3 prime. This is the segment 2 prime. That's 2. This is 3. Okay. And then what you do is take the mirror image about the real axis. Or you could just continue around here. That's still going to be infinite. And come up starting at large negative frequencies, moving up. Negative frequencies, this is still going to be positive, so it's still going to be negative, okay? Omega starts out very large, negative, that would be very small, so it starts out here. As omega decreases, this is going to increase, so it's going to move out like that. And so then this segment here is going to map into this segment here. So all I've really done, you could just take a look at it, map the points above the horizontal axis. That gives this, and that. Then take the mirror image, it's going to give you that and that. Okay. Notice that the -1 point, it always goes through the -1 point. So there is no gain k that you can adjust it such that it avoids the -1 point. It always goes through the -1 point. So it's always marginally stable. And so again, what we'd like to do is stabilize it. You could use, so this is the root locus for this. How about if we put an s plus 1 in there, s plus 1. All right, what that does is it contributes a 0. So we have a 0 over here at -1. How does that affect the root locus? It attracts it, right? So instead of it being along the horizontal, the vertical axis here, it's going to break away, right? And it's going to have these 2 branches here, and then 1 branch here, 1 branch there. It begins at the open loop transfer function poles, terminates at the open loop transfer function zeros, 1 finite 0 and 1 0 at -infinity. Okay, so you have stabilized the system, and notice that there is no, it's never marginally stable. It's never marginally stable for any value gain k greater than 0. It is, the poles will always be in the left-hand plane. System will always be stable for any positive value gain k. And so what we'd like to do is modify the Nyquist diagram to correspond to that, the addition of that lead compensator there. This S-plane contour is the same. And in fact, the analysis, when you put the rho e to the j theta plus 1 in there, in the numerator, you're still letting rho go to 0, so this goes away. So it gives you exactly the same thing here, okay? In other words, you still get this contour here in the GH plane, okay? And then the question is, what happens in this segment here such that the system becomes stable, right? You can see that it's stable, okay? So we want to take a look at this other frequency response plot that it had. It's what I call it 2. So just actually you get 2 to look at the frequency response. Okay. Okay, so we have the frequency response there. Notice that there's the root locus. Um, Notice that the phase, the magnitudes start very large with a phase right around minus 180. In other words, it starts right around this point right here. And it's the magnitude is decreasing, getting smaller and smaller. And the phase is going from minus 180 to minus 90. Okay, through minus 135 to minus 90. So what's happening is that it's doing something like this. Coming in like that. Okay. And the rest of it, what's the rest of it look like? In other words, this segment here again maps into the origin. Right? So this is our 2 prime. Now we just take the mirror image of this diagram here. In fact, this is not here until I take the mirror image, right? So it's going to be like that, right? So this is directed like that, that's directed like that, right? So it kind of starts out like that, comes in like that, goes around like that, around like that. The minus 1 point is in here. Notice that there is no, for all positive values of gain k, the root locus will look like this, basically like this. In other words, the minus 1 point will always be how many net clockwise encirclements of the minus 1 point do we have? 0, right? We have, if you start here, you've got 1 counterclockwise, and you've got to continue, right? And you've got 1 clockwise, so n equals 0. So n equals minus 1 plus 1 is equal to 0. P, what is P equal to? The number of open loop transfer function poles in the right half plane. 0. So Z is equal to 0. And the system is stable for all positive values of gain k. And you can see it here from the Nyquist diagram, right? For any positive value gain k, the closed loop transfer function poles would be in the left half plane. And here, by applying the Nyquist stability criterion, once you have the Nyquist diagram, you can find n. From the open loop transfer function, you can find P, no right half plane poles, therefore Z is equal to 0, and therefore the system is stable. There's no possibility for this system to be marginally stable, right? Because it never will pass through the imaginary axis.
You're saying not even when k is 0?
Well, k equals 0. You have to have some
k, okay.
gain.
So
K.
whenever it starts out, it's already in the left half.
Yeah.
Okay.
You have to have some gain for the system to operate.
Right. Okay.
And so there are other diagrams. Let me just, I won't take long, but if you have a system like this, we have now an S plus 5 and an S minus 1 squared. Okay. And we have negative feedback. Let's take a look at the root locus here for this first. Okay, so it's always nice to look at the root locus plot when you're dealing with Nyquist. Okay, so the root locus, you have 2 poles at 1, 2 poles at right here at 1, and you have a pole at minus 5, say over here minus 5. And a 0 at minus 1. So the question is, where does a root locus exist on the real axis, right? Doesn't exist there. Remember, there are two poles there. So it will exist here, right? It exists there, and it's always going to be directed away from that pole towards that zero. Okay. Then asymptotes. How many asymptotes does it have, right? This is S cubed, this is S, 2 asymptotes, right? When you have two asymptotes, the angles are going to be 90 degrees, plus and minus 90 degrees, right? And then the origin of the asymptote. The origin of the asymptote is the sum of the pole locations. You've got 1 plus 1 minus 5 minus the sum of the 0 locations divided by the difference between the number of poles and zeros. So you've got, what is this? Plus 1, so it's 3 minus 5 is minus 2 over 2 is minus 1. So here is the what do you call it? The origin of the asymptote, and the angles are plus and minus 90 degrees. And so this, what's going to happen is that you're going to have breakaway from there. As gain k increases from 0, it's going to break away. One is going to go towards that asymptote, and one towards that asymptote. You have 3 branches, right? Third order denominator, 3 branches, 1, 2, 3. There's a possibility for marginal stability in this case, right? What you can do is use the Ralph-Hurwitz stability criterion to determine the gain k for marginal stability. And then if you have k equal to 1, you're just going to squeeze it down or expand it accordingly. To find, in other words, if k equals 1, right, you can either compress it or expand it to find the actual 180-degree phase crossover point, like we did in the previous example. Okay. And so what this is going to look like in this case is this. We have to route around. Actually, we don't have to route around because we don't have any poles at the origin, right? No poles at the origin. So this, in that case, it just goes straight up, right? Straight up like that, and around like that. Okay. So this is going to start out at a finite value there. A finite value. In other words, when omega is equal to 0. When omega is equal to 0, right? Replace S by J omega, you can find what with omega equals 0, you find that that's the finite value there, and it's going to wrap around like this. When you take a look at the frequency response for this system, it maps up like that, comes in like this, and then comes around like that. So this is, and this crossover point for the case where k equals 1 is going to be minus 1.25. Okay, and like I said, this point here you can determine it through the by finding the gain k for marginal stability, and then expand or contract so that k is equal to 1. Okay. And this system here, the minus 1 point is right there. Okay. What is the value of n here? You can start here, counterclockwise. N is equal to what? Minus 2. P is equal to what?
Poles, right?
So the number of right half plane poles is 2. Z is equal to 0. you can see that the system is marginally stable. If the gain K is decreased, if the gain K is decreased, this -1 point at some point will not have two encirclements. Right? In fact, won't have any encirclements. In fact, the n will be equal to 0 and p will be equal to 2, and therefore z will be equal to 2. Okay. So, again, it's good to look at the root locus plot. You can see that it will be marginally stable, and therefore it will have a 180-degree phase crossover point there. I have diagrams that are produced by MATLAB. I can show you those next time. So go ahead. If you have questions about that homework, let's get them straight by the time next week sometime. And no really new material to present. The review for the test?
For the past
The
test,
results,
yeah.
I said I would give them before the